Good morning, guys. Today we're going to look at linear programming. We've been working with solving systems of equations, systems of inequalities. Linear programming just puts those two ideas together. Now, as you can see, linear programming is the maximizing or minimizing of a linear function. We call that the objective quantity, and that objective quantity is subject to a system of linear inequalities or equations, which we call the constraints. For example, say we are producing two products and we want to minimize the costs associated with those products. So the cost would be the objective quantity, and then the restrictions on the products. We produce a certain amount of each type of product. Those would be the constraints, and we put all that together in this linear programming problem to be able to figure out how many of each type of product we could produce while still minimizing our objective quantity, which we're going to call the cost. So let's look at the process and work through a few examples. Okay, guys. Here we have an example of a linear programming problem that wants us to find the maximum and minimum values of c equals 4x plus 5y. So this is our objective quantity given the following constraints. And here's our list of constraints. A lot of times you may just say find max or min of this right here. And they'll be written like this for the most part. So as we're going through, first thing we want to do is I want to graph the constraints. If I want to figure out what point is going to produce the largest value of this, I got to figure out what points I'm allowed to plug in, what points I'm allowed to work with. And same if I want the minimum value of this. Because only values that satisfy this system are allowed to be used in our objective quantity. So first we're going to solve the system of inequalities, which we do by graphing the system. So as I go through and graph, I always like to label my lines first. It'll keep everything organized here in a minute. So I'm just going to call the first one line 1, line 2, line 3. So as I go through, x is greater than or equal to 0. We graph the line x equals 0. The greater than, less than stuff, all that does is affect the shading. So we'll just graph the lines first. So x greater than or equal to 0, I go to 0 on the x-axis, and I draw the vertical line, which is the y-axis. So that's the line x equals 0. For y equals 0, I go to 0 on the y-axis, and I draw a horizontal line through it, which happens to be the x-axis. That's going to be my line 2. So that's y equals 0, x equals 0. Remember, x equals 0 is all points that have 0 for the x-coordinate, which is going to be all the points on the y-axis. Y equals 0 is all points that have 0 for the y-coordinate. So that's all the points on the x-axis. They have no height, so no y. Next, we're going to graph this third equation. If you're not sure, just looking at the equation, you can always subtract your x over, put it into slope-intercept form, but you can probably do that one quickly by x-intercepts. X is 6, y is 6, so we can just go to 6 and 6. Or if you went slope-intercept form, 6 for the y-intercept, slope is down 1 over 1, down 1 over 1, down 1 over 1, and it puts us all the way out here. So there's my third line. We'll pretend that it's straight. And that's going to be line 3. Move this over here. Now we're going to use the inequalities. Okay? Now we want to figure out, I've got a lot of stuff going on here. What part of this is my answer choice is going to come from? So for line 1, x is greater than or equal to 0. Well, the greater x's, are they going to be to the left of the line or the right of the line? Greater numbers on the number line are to the right. So the greater x's are to the right of our line. So I just do these little arrows here because I don't want to shade all over this thing and then try to figure out what's going on. So I'm just going to use a little arrow to indicate it could be in this area, or that area. For line 2, y is greater than or equal to 0. So that's a horizontal line. It's a y equals line, so we don't think left and right. We think above or below. So our greater y values above or below the line? They're above the line. Positive y's are up here. They're greater than your negative y's, which are down here. So since we want all the y's that are greater than 0 or greater than or equal to, we want all the positive y's. So it could be here, here, or there. So starting to get an idea of what area we're going to be working with. And the last one, y is less than or equal to negative x plus 6. Less than y's, again, y's are above or below. So our lesser y is going to be above a line or below the line. They're going to be below the line. So we're going to shade below the line. Now you get a really good idea of what area we're going to be working with here. And it's the area that has arrows or shaded values for all three inequalities. So in this problem right here, that would be this triangle right here. And I'll tell you, more times than not, it's going to be inside the shaded or inside that closed figure, that shape, whatever it happens to be. But that's not always the case. There are times that we could be up here, okay, or we could be down here, down here, down here. It doesn't matter. Okay? This particular problem, which is the most common type, it was inside. So we're looking at this area right here. We call this area the feasible region, which makes sense. Feasible meaning possible, so or possible and making sense. The only answers, the only points that could possibly satisfy all these inequalities come from in here. So those are the only points that could possibly go into here. Those are the only points that are feasible for this objective quantity given these constraints. We just call that the feasible region. These corner points, which I will label them point 1, point 2, and point 3, just trying to help keep organized. We call those vertices, which y'all should remember that from geometry. A vertex is where you have two lines crossing. So that's the corner points of your geometric figure. So those are your vertices. Next step, after we've identified our feasible region by graphing and solving our system of inequalities, we want to identify those vertices. Because the way linear programming works is the maximum values can only occur at the most extreme points. That goes for minimum values also. So the optimal values, ones that are going to give us a maximum or minimum, can only occur at the vertices. So that's the next step in the process. We're going to identify those vertices. So let's come over here. Get rid of that. So I got some room to work. And let's just look at point 1 is the intersection of what two lines? Line 1 and line 3. And well, we know right here line 1 is x equals 0 and line 3 is x plus y equals 6. Well, no, you're saying that line 1 is x greater than or equal to 0. Line 3 is x plus y is less than or equal to 6. Why do I not need the inequalities there? Why do I have those as equal signs? Well, it's because we're talking about the points on the line. Inequality talks about shading one side of a line or another, above or below, left or right of a line. When we're looking at the actual points on the line, that's the equal to. So we want to know where these 2 points, what point on the two lines are in common. So we're going to just look at where they're equal. Well, you go through and solve. X coordinate is 0. Well, if my x coordinate is 0, my y coordinate has to be 6. So 0, 6 is my first point here. Let's look at point 2. Point 2 is the intersection of which two lines? Line 1 and line 2. Now, I know we're writing a lot of stuff. It's very important to keep this organized so you get the correct lines intersecting and you get all your information in the correct order. So again, line 1, x equals 0. Line 2, y equals 0. Well, there it is. There's your ordered pair. Let's try to make them look like zeros. Is 0, 0. And this is just an arrow for those of you who didn't catch that. P3, point 3. Point 3 is intersection of which two lines? Line 2 and line 3. So line 2, y equals 0. Line 3, x plus y equals 6. So on this one, now we have the y coordinate is 0, and the x coordinate when y is 0 has to be 6. So those are my 3 points. Those are the only possible answers that can give me a maximum or minimum value. So those are the vertices. We've identified the feasible region. That was step 1. We identified our vertices. That's step 2. Now we test them out. We see which of those is going to give us a maximum value, and which one's going to give us the minimum value. So let's look. And I always write it this way. I'm going to start using function notation. So the C function with P1 as my variable. So C of P1, C of P2, and C of P3. Well, the C function is 4 times something plus 5 times something, something different. So that doesn't change no matter what point I'm plugging in. 4 times the x coordinate plus 5 times the y coordinate. 4 times the x coordinate plus 5 times the y coordinate. 4 times the x coordinate plus 5 times the y coordinate. That's why I write it in this manner. Helps keep it organized. That's why we're putting the P1s there. That's why we're putting the L1s. It lets us transition neatly and in an organized manner from one step to the next. So now we just plug in. P1 is 0, 6. So 0 goes in for the x. 6 goes in for the y. P2 was 0, 0. 0 for the x, 0 for the y. P3 was 6, 0. 6 for my x, 0 for my y. We do the arithmetic. 0 plus 30 is 30. 0 plus 0 is 0. 24 plus 0 equals 24. Now look at the question that's asked. The question said find the maximum and minimum. So at this point, we've got to know, is my answer my point, or is my answer what I got it to equal? So what do you think? If I'm finding the maximum and minimum, are we identifying a point, or are we identifying a value? We're identifying a value. And I don't want the points. If they had wanted the points, they'd have said, what point produces a maximum, or what point produces the minimum? They just said, what is the maximum? So of these 3 values, the maximum is 30. So the highest this equation can ever be, given these constraints, is 30. And the minimum in this case would be 0. Because the smallest that this value can ever be, given only using points from this system of inequalities, is 0. So maximum and minimum. If they had said, find the point that produces a maximum, then we would write the ordered pair 0, 6. Or if they had said, find the point that produces a minimum, we would write the ordered pair 0, 0. But we've got to make sure you're paying attention and answering the question that is asked. So let's kind of recap and go through write out our steps. For solving a system, or a linear programming problem, rather. Solving a linear programming problem. So step 1 is graph the constraints. To identify the feasible region. Next thing we did, we identified the vertices. Of the feasible region. Now when you do that, sometimes you can just look at the graph and tell. This example, we could have looked at the graph and told it wouldn't have been complicated. But when you get more and more lines in there and they're out in space instead of on the axes, as far as your intersection points, your vertices go, you'll need to be very careful and just very thorough as you go through, because you'll want to use your solving strategies, whether it be linear combination or substitution. I did substitution on those because they were real small. You may have to do some linear combination to get some of those intersection points. But the idea is to identify those intersection points, which are called the vertices. Once we've got those vertices, final step is evaluate the objective quantity at each vertex. Evaluate the objective quantity at each vertex. And from there, you're just looking for biggest number or smallest number, depending on what they're asking for, maximum or minimum, or the point that produces a maximum or minimum. So that's linear programming in a nutshell. The way the problem can be asked, it can be asked any number of ways, but the process is going to be the same. Once you've identified what you're trying to maximize or minimize, that's your objective quantity. Once you figure out the limits on the variables for that, then those are your constraints, and you'll just go through those 3 steps like we just talked about. So the process doesn't change once you get the problem set up. Just keep in mind, when you see the words maximize or you see the words minimize, you need to be thinking this is a linear programming problem. So what is it I'm trying to maximize or minimize? That's my objective quantity. What are the restrictions on the variables of that objective quantity? And those are going to give you your constraints. You just go straight through those 3 steps from there. I'll see you in class tomorrow, guys.